Our universe is held together by a hidden architecture, a cosmic web of immense filaments. These threads of dark matter and hot gas form the largest structures in existence, yet they remain almost entirely invisible to our eyes. By the end of this journey, you will understand the 25 greatest mysteries locked within these cosmic threads. We will explore why most of the universe's ordinary matter has vanished and question if the fundamental laws of physics are the same inside these vast, empty corridors. What single cosmic mystery makes you wonder the most? This vast cosmic architecture remains almost entirely hidden from our direct view. How can the backbone of the universe itself be so elusive? The answer lies in its composition. These filaments are not made of stars and bright gas alone. They are primarily constructed from dark matter, a substance that does not emit, absorb, or reflect light, and are laced with incredibly hot, thin gas that glows only in X-rays, a light our eyes cannot see. To map this invisible framework, astronomers have become cosmic detectives, employing ingenious methods. One key technique is gravitational lensing. They observe how the immense gravity of a filament warps the light from galaxies behind it, much like a fingerprint left on glass. By measuring this subtle distortion, they can trace the otherwise unseen mass. Another method involves charting the precise positions of millions of galaxies, revealing how they are strung along these dark threads like pearls on a string. Yet despite these clever tricks, directly observing the faint, hot gas within the filaments remains one of the greatest challenges in modern cosmology. We are essentially trying to photograph a ghostly spiderweb from a million light-years away, using instruments that are only just sensitive enough to see its faintest shimmer. But the invisible nature of these filaments points to an even deeper secret. The very skeleton of the cosmic web is thought to be built from dark matter. This mysterious substance, which does not interact with light, provides the gravitational foundation for everything we see. Think of a magnificent, intricate cathedral. You admire the stained glass windows and the soaring arches, but the entire structure is held up by a hidden framework of steel and stone. Dark matter is that framework for the universe. Its immense gravity is the invisible hand that sculpted the primordial soup of the early cosmos into these vast, interconnected filaments. It drew ordinary matter, the gas that would eventually form galaxies, into its web. For decades, this has been the prevailing theory, a ghostly skeleton giving shape to the visible world, yet a profound question remains. If dark matter truly forms the backbone of these cosmic threads, why have we never detected a single particle of it? The search for direct proof continues in deep underground laboratories and with powerful particle colliders, all hoping to catch a glimpse of this elusive substance. Finding it within the filaments themselves would be the ultimate confirmation, like finally touching the invisible steel that holds up the sky. This quest defines one of the greatest challenges in science, forcing us to question whether we truly understand the fundamental ingredients of reality. This invisible framework holds the answer to one of cosmology's most puzzling cases, the mystery of the missing universe. When we add up all the normal matter, the atoms that make up every star, planet, and our own bodies, we find that more than half of it is simply gone. Our best models of the cosmos tell us precisely how much of this ordinary matter, called baryonic matter, should exist, yet when we look, we cannot find it. So where did it all go? The prime suspect is the cosmic web itself. Astronomers theorize that these missing atoms are hiding in the vast, empty-looking corridors between galaxies, woven into the filaments as an incredibly thin, superheated gas. They call this elusive substance the warm, hot intergalactic medium, or the WIM for short. Imagine a steam room so vast it stretches between galaxies, filled with a fog 1,000,000 times less dense than the air we breathe, yet heated to temperatures of millions of degrees. This gas is so diffuse it does not glow in visible light, and so hot it only emits a faint whisper of X-ray energy. making it nearly impossible to detect with our current telescopes. To find this cosmic ghost, scientists have turned into master sleuths. They use the brightest objects in the universe as flashlights, quasars whose brilliant light shines through the cosmic web. As this light travels through the WIM, the specific elements within that hot gas, like oxygen and neon, absorb very particular colors from the quasar's light, leaving behind a unique fingerprint. By analyzing these faint absorption lines, astronomers can confirm the presence of the WIM and finally account for the universe's missing atoms. It is a cosmic treasure hunt on the grandest scale, searching for a shadow that holds the key to the very stuff we are made of. Finding the missing atoms only deepens the cosmic puzzle. How did such an intricate web of matter ever emerge from the formless fire of the Big Bang? In the very beginning, our universe was a nearly smooth, searingly hot soup of particles. There were no galaxies, no stars, and certainly no vast connecting filaments. For these immense structures to form, the cosmos needed a seed, a blueprint. That blueprint was written in the faintest of imperfections. Imagine a perfectly still, silent lake. Now imagine tossing a single grain of sand into its center. The ripples that spread out are tiny, but they create a pattern across the entire surface. In the infant universe, similar ripples existed, minuscule variations in density, places that were ever so slightly denser or thinner than their surroundings. These primordial wrinkles were the seeds from which everything, including the cosmic web, would grow. But a seed needs a force to make it grow. That force was gravity, driven primarily by the invisible hand of dark matter. In the denser regions, dark matter's gravity began to pull, drawing in more and more material over hundreds of millions of years. This created a cosmic tug of war. The densest knots collapsed to form the first galaxies and galaxy clusters, while the matter in between was stretched into long, bridging tendrils, the filaments of the cosmic web. We can see this process unfold in supercomputer simulations that model the evolution of the universe, and they show a web slowly knitting itself together over billions of years. Yet a fierce debate continues about the exact timeline of this growth. Did the web form quickly in the universe's youth, its filaments snapping into place like cosmic rubber bands, or was it a slower, more gradual process with the great walls of matter steadily thickening over eons? The answer holds the key to understanding the true strength of dark matter and the ultimate fate of the universe's largest structures. We are left watching a movie of cosmic construction, but we are still unsure if it played out in a rapid burst or a patient, drawn-out epic. These cosmic filaments are more than just a static framework. They act as the universe's vital supply routes, feeding galaxies the fuel they need to thrive. Within these dark threads, astronomers believe rivers of cold gas flow silently through the void. This is not the thin, superheated WIM, but a denser, cooler material that acts as the primary fuel for star formation. Picture a great river system on an unimaginable scale, with currents of hydrogen and helium streaming along the filaments, guided by gravity toward the hungry galaxies clustered at their intersections. When this cold gas reaches a galaxy, it provides the raw material needed to collapse under its own gravity and ignite into brilliant new stars. Without this constant delivery of fresh fuel, many galaxies would exhaust their gas reserves and fade into darkness, their stellar fires extinguished. This theory elegantly explains why galaxies located at the busy crossroads of filaments within vast galaxy clusters are often the most active and brightly shining. They are positioned at the terminus of the cosmic web's most powerful rivers, receiving a constant, rich influx of material. Yet observing this process directly presents a monumental challenge. The gas itself is dark and cold, emitting very little light for our telescopes to catch. We are trying to spot a faint, flowing river in the pitch black of an intergalactic night. The best evidence we have is indirect, like finding a wet trail leading to a well-watered garden. We see the result, the vibrant star formation in galaxies, and we trace the path back along the filamentary structures that connect them. But catching the river in the act of flowing, witnessing the gas as it streams into a galactic disk, remains one of the most sought-after observations in astronomy. It would confirm that the cosmic web is not just a beautiful structure, but a living, breathing circulatory system for the entire universe. Deep within these vast, empty corridors, another hidden force is at work. The voids between galaxies are not truly empty, they are threaded with immense, invisible magnetic fields. How can such powerful fields exist in a space so devoid of matter? Their presence is a profound enigma. One leading theory suggests these cosmic magnets were born in the universe's violent infancy from the turbulent plasma of the Big Bang. Tiny seed fields, weaker than a refrigerator magnet, could have been stretched and woven through the expanding cosmos by the very same motions that sculpted the web. As the filaments formed, these magnetic threads were pulled along with the gas, concentrating and amplifying them within the dark tendrils. Another possibility points to the galaxies themselves. When stars explode as supernova or when matter spirals into supermassive black holes, they can blast out winds of charged particles, seeding the intergalactic void with magnetic energy that then travels along the cosmic highways. Detecting these fields is a monumental task. Astronomers look for a subtle effect called Faraday rotation, where the magnetic field twists the polarization of light from distant radio galaxies as it passes through a filament. It is like trying to measure how a gentle breeze distorts the view through a million-mile thick pane of glass. The existence of these fields challenges our understanding of physics in extreme environments. They could play a crucial role in guiding those rivers of cold gas, or even accelerating particles to near light speed, creating cosmic rays that travel across the universe. Their very presence in the near-nothingness of a filament forces us to ask if we are missing a fundamental piece of the cosmic puzzle, a hidden law that governs the void itself. This intricate relationship between filaments and galaxies raises a profound question. Why do some of these cosmic threads glitter with stellar cities while others stretch through the darkness, seemingly empty and barren? The answer appears to be written in the very properties of the filament itself. Its mass, its density, and even its geometry all act as a cosmic blueprint, dictating the fate of the galaxies that form along its length. A thick, massive filament, heavy with dark matter, creates a powerful gravitational well. This deep well pulls in vast quantities of gas, providing a rich and continuous fuel supply for star formation. Galaxies born in such fertile environments are often destined for a life of vibrant activity, growing large and luminous. In contrast, a thin, wispy filament possesses a much weaker gravitational pull. It gathers less gas, creating a starved environment where any nascent galaxies struggle to gather enough material to shine brightly. They remain small, faint, or may not form at all, leaving the filament to appear as a desolate bridge in the void. The geometry of the web is equally important. A straight, direct filament acts like a wide cosmic freeway, allowing cold gas to flow efficiently toward the waiting galaxy clusters at its ends. But a filament that is twisted or kinked creates a turbulent, inefficient path. The gas crashes into itself, heating up and stalling, much like a traffic jam on a winding road. This can starve the central galaxies of the cold fuel they crave, stifling their growth. We see this pattern reflected across the universe. The most massive and brilliant galaxy clusters are almost always found at the nodes where several thick, robust filaments intersect, a testament to the abundant resources delivered from all directions. Yet a deeper mystery persists. Why do two filaments with seemingly identical mass and structure sometimes host completely different families of galaxies? This suggests that a galaxy's fate is not solely determined by its address in the cosmic web. Other, more local factors must be at play, like the violent feedback from supernova explosions or the intense radiation from a supermassive black hole at a galaxy's center, which can heat or blow away the incoming gas. The connection is a delicate cosmic dance, a push and pull between the large-scale architecture of the universe and the chaotic, local physics within each galaxy. Understanding this dance is key to unraveling the entire story of how a galaxy like our own Milky Way came to be. The destiny of these great cosmic rivers is written in a battle between two invisible forces. On one side, gravity relentlessly pulls matter inward, thickening the filaments and drawing galaxies closer together. On the other, dark energy pushes the universe apart, creating an expansion that grows stronger with time. For billions of years, gravity has held the upper hand, patiently weaving the web into the structure we see today. But this struggle is not eternal. As dark energy continues its accelerating push, the future of the filaments grows uncertain. One possible fate is a slow and quiet dissolution. Over trillions of years, the accelerating expansion of space could stretch the filaments so thin that they effectively evaporate. The rivers of gas flowing along them would be severed, isolating galaxies in a vast and ever-cooling emptiness. Star formation would cease everywhere, and the universe would grow dark and silent. Another, more violent theory suggests a great rip. If dark energy's strength increases over time, it could eventually overcome not just the expansion of space, but the very forces holding matter together. In this catastrophic endgame, the filaments, the galaxies within them, and even atoms themselves will be torn asunder. There is a third, more subtle possibility. Perhaps the web will not vanish, but instead evolve into a new and unrecognizable structure. As the universe expands, the largest filaments may be the last to hold on, condensing into immense, isolated chains of surviving galaxies, like glittering islands in an infinite, dark ocean. These final structures would be the last vestiges of a connected cosmos, a ghostly echo of the vibrant web that once was. The ultimate fate of the filaments is therefore tied to the deepest mystery in cosmology, the true nature of dark energy. Is it a constant force or is it changing? The answer will determine whether the universe's grand architecture endures, transforms, or simply fades away into nothing. The silent architecture of the cosmic web may hold an echo of the universe's first and only sound. This echo is not carried by air, but is frozen into the very distribution of matter, a direct relic from the cosmos's fiery birth. Just moments after the Big Bang, the universe was a seething, dense plasma, a fluid of particles and light. In this hot soup, gravity would pull matter inward, while the intense pressure of radiation would push it back out. This created a rhythmic pulse, a series of pressure waves that traveled through the primordial cosmos like sound waves moving through air. These are the Baryon acoustic oscillations, the ringing of the newborn universe. As the universe expanded and cooled about 380,000 years after the Big Bang, it underwent a dramatic change. Atoms formed and light previously trapped was suddenly set free. This released light is what we now observe as the cosmic microwave background, the oldest light in the universe. The frozen sound waves, however, left their permanent signature. Each wave created a spherical shell, a ripple in density where matter was slightly more concentrated. Over billions of years, these shells of excess matter became the preferred locations for galaxies to form. The radius of that original shell became a standard ruler etched onto the fabric of space. This is where the filaments of the cosmic web enter the story. They are not randomly placed. The great walls and threads of galaxies we see today are the grown-up versions of those ancient density ripples. When we measure the large-scale structure, we find that galaxies are more likely to be separated by a specific distance, a cosmic echo of that first sound wave's size. By mapping the filaments and the distances between galaxy clusters along them, astronomers are essentially measuring the fossilized imprint of the Big Bang's resonance. It is a pattern that allows us to understand the properties of the early universe with incredible precision, from its composition to its expansion rate. So the next time you look at a map of the cosmic web, remember you are not just seeing structure, you are hearing a ghostly whisper, the fading note from the universe's very first song. But this cosmic supply line is a two-way street. The very galaxies that feast on the filaments also send powerful messages back into the void. These are the whispers of filamentary feedback, a cycle of creation and destruction that shapes the web itself. When a galaxy consumes the cold gas flowing along a filament, it does not do so quietly. The process is violent and energetic. Massive stars live fast and die young, exploding as supernova. These colossal blasts eject vast amounts of enriched material and torrents of energy back into the surrounding space. On an even grander scale, the supermassive black holes at the centers of many galaxies can awaken, becoming active galactic nuclei. As matter spirals into these gravitational monsters, it heats up to incredible temperatures, releasing intense radiation and powerful jets of plasma that can punch far out into intergalactic space. This ejected energy and matter does not simply vanish. It slams back into the filament that originally fed the galaxy. Think of a tree drawing water from an underground river, only to have its roots occasionally release a blast of heat and chemicals back into the soil, altering the river's very composition. This galactic feedback can have two profound effects. It can heat the surrounding gas within the filament, preventing it from cooling down and flowing smoothly to fuel future star formation. In essence, the galaxy is scorching the land that provides its food. In more extreme cases, the outflows can physically push the gas away, clearing vast bubbles within the cosmic web and effectively severing the supply line, not just for that galaxy, but for its neighbors as well. This creates a self-regulating cycle. A galaxy experiences a burst of growth which triggers a violent outburst, which then shuts down that growth by disrupting its fuel source. It is a delicate balance between feast and famine, governed by the echoes of stellar death and black hole fury. The question for astronomers is whether this feedback is a gentle whisper that merely regulates growth, or a cosmic shout that can permanently resculpt the architecture of the universe's largest structures. This galactic feedback creates a chaotic and unpredictable environment, leading to one of the most practical puzzles in mapping the cosmic web: the wildly inconsistent temperatures found within its filaments. Why does one part of a cosmic thread feel like a deep freeze while another simmers at millions of degrees? The answer lies in a battle between heating and cooling processes that rage across these vast structures. On one hand, you have the cold flows, rivers of pristine hydrogen and helium gas that have remained relatively untouched since the early universe. These streams are the lifeblood for galaxies, cold enough to collapse and form new stars. Yet sharing the same cosmic corridor is the warm-hot intergalactic medium, a gas so hot it glows faintly in X-rays. This incredible heat comes from multiple sources. As galaxies and galaxy clusters form at the intersections of filaments, their immense gravitational pull accelerates any infalling gas. When this gas smashes into the denser material already in the cluster, it creates a colossal shock wave, like a sonic boom on a cosmic scale, heating the gas to extreme temperatures. Meanwhile, the violent feedback from supernova and active black holes within galaxies pumps tremendous energy back into the surrounding filament, creating vast heated bubbles. This results in a filament that is not a uniform tube, but a turbulent and patchy structure. It is a cosmic version of a river system where freezing glacial meltwater flows alongside boiling hot springs. This uneven temperature distribution is critical because it directly controls the fate of galaxies. If a filament is too hot, the gas becomes too energetic to coalesce and flow smoothly. It simply cannot cool down enough to fuel star formation. A cooler filament, however, acts as an efficient pipeline, delivering cold gas directly to a galaxy's core. The mystery deepens when we realize that our observations of these temperatures are incredibly difficult to make. We are essentially trying to take the temperature of a ghostly, wispy thread from billions of light years away, with our measurements often giving us a confusing average rather than a detailed map of its hot and cold spots. Understanding this thermal chaos is essential, for it dictates the rhythm of birth and death across the entire cosmic web. This grand cosmic architecture is not a permanent fixture. The same filaments that define our universe are locked in a silent, cosmic tug-of-war with its most mysterious component, dark energy. We can think of the web as a patient weaver, constantly working to pull matter together through gravity. But dark energy is an unstoppable force working in the opposite direction, stretching the very fabric of space itself and accelerating the universe's expansion. For billions of years, gravity has dominated, allowing the web to form and mature. Now, the balance of power is shifting. As dark energy's influence grows, it begins to pull on the threads of the cosmic web. The vast, empty voids between filaments are expanding at an ever-increasing rate. This stretches the filaments, making them longer, thinner, and more tenuous. It is as if the loom on which the universe is woven is itself being steadily pulled apart. The rivers of cold gas that flow along these threads may find their currents slowing, their paths to galaxies lengthening and eventually being severed. This is not a distant, abstract future. Astronomers are already searching for the fingerprints of this struggle in the large-scale structure we observe today. By meticulously mapping the distances between galaxies and the thickness of filaments across cosmic time, they hope to measure the precise influence of dark energy. Does it act as a constant force, or is its strength changing? The answer is written in the gradual thinning and eventual dissolution of the cosmic web's grand design. This makes the filaments themselves one of our most powerful tools for understanding the force that will ultimately determine the fate of everything. The web's slow unraveling is a direct message from the void, a clue to the deepest mystery in the cosmos. Buried deep within the modern cosmic web are the ghosts of its very first structures. To find them, we must journey back to the cosmic dawn, a time when the first stars and galaxies were just beginning to flicker to life. These primordial filaments were the universe's earliest skeletal framework, thinner and more fragile than their modern descendants. They formed from the purest, most pristine gas, untouched by the complex elements forged in later stars. So how could we ever hope to see such ancient, faded threads? Their detection relies on hunting for subtle signatures that have traveled across billions of years to reach us. One promising method involves searching for a specific wavelength of light emitted by neutral hydrogen gas as it was energized by the first brilliant sources of ultraviolet light. This emission, stretched by the expansion of the universe into long radio waves, could trace the faint, wispy outlines of the earliest filaments. Another clue might be found in the way these first structures gravitationally lensed the even more ancient cosmic microwave background, leaving minuscule, twisted imprints on the oldest light we can see. Next-generation observatories are being designed specifically for this cosmic archaeology. Gigantic radio telescope arrays with thousands of antennas spread across deserts and plains will scan the skies for that faint hydrogen signal. New space telescopes, sensitive to infrared light, will peer through cosmic dust to see the first galaxies being born along these dark threads. Finding a primordial filament would be like discovering the foundation stone of a vast, ancient city. It would show us the universe in its simplest, most elemental form, a blueprint before the chaos of stellar life and death began its complex work. This search pushes our technology to its absolute limits, asking it to trace a whisper from the edge of time itself. What secrets about the universe's raw beginnings are locked within those first, faint strands? The great walls of the cosmic web do more than connect galaxies, they define the shape of emptiness itself. Surrounding these filaments are the voids, unimaginably vast regions of space that appear almost completely empty. But these voids are not random holes, they possess a startlingly specific geometry. Most are not irregular blobs, but rather rounded, bubble-like spheres or gently sloping polyhedrons, their shapes sculpted with mathematical precision. This is the mystery of the void. How can nothingness have such a distinct form? The answer lies entirely with the walls that contain it. The dense filaments and galaxy clusters act like a rigid scaffold, pressing inward and defining the void's boundaries. Picture a cosmic foam where the soapy films are the luminous filaments and the air inside each bubble is the void. The structure and strength of the films dictate the size and shape of the empty space they enclose. A region surrounded by thick, robust filaments will be compressed into a smaller, more regularly shaped void. An area bounded by weaker, more tenuous walls might expand into a larger, more irregular emptiness. This relationship is a delicate cosmic balance. The voids, in their own passive way, also exert an influence. As the universe expands, these empty regions grow faster than the denser web, effectively pushing the filaments apart and stretching them into the great walls we observe. It is a silent dialogue between something and nothing, where the architecture of everything defines the geometry of the void, and the growth of the void, in turn, stresses the cosmic architecture. This leads to a profound question: why are there no truly giant voids? Why does the cosmos seem to prefer a specific maximum size for these empty regions? The answer may be locked in the initial conditions of the universe, in the amplitude of those primordial ripples that first seeded the web. If the ripples had been smaller, the voids might have grown to consume everything. If they had been larger, the web might have been a dense, tangled knot. The precise geometry of nothingness, therefore, is a fossil from the Big Bang, a cosmic signature telling us that even emptiness has rules and a form. These silent, invisible threads may be the most powerful particle accelerators in the entire cosmos. The immense shock waves generated when filaments collide or when gas flows slam into galaxy clusters can accelerate subatomic particles to velocities approaching the speed of light. These particles become cosmic rays, high-energy messengers that bombard our planet from the depths of space. A single one can carry the energy of a professionally thrown baseball, all compressed into a tiny, fast-moving particle smaller than an atom. The process works like a natural version of the Large Hadron Collider, but on an unimaginably grander scale. Within a colliding filament, particles can bounce back and forth across a shock wave's turbulent front, gaining a little more energy with each crossing until they are finally ejected into the void. Yet proving this theory is a monumental challenge. When these cosmic rays finally reach us, their paths have been twisted and scrambled by the magnetic fields they have passed through. It is like trying to find the source of a single, specific leaf that has blown into your yard after a storm, with no way of knowing which tree it came from or how far it has traveled. We can detect the particles, but we cannot easily trace them back to their origin point within the cosmic web. This mystery has profound implications. If filaments are indeed these powerful accelerators, they could be the source of the most energetic particles ever observed, whose origins have puzzled scientists for decades. Understanding this process would open a new window into the most violent and energetic phenomena in the universe, all happening within the seemingly quiet and empty corridors of the cosmic web. These silent rivers of hot gas could be testing the laws of physics themselves. Scientists propose that the cosmic web's filaments offer a unique laboratory to answer a startling question: have the fundamental constants of nature always remained constant? These constants are the immutable numbers that govern the universe, like the fine structure constant which dictates the strength of electromagnetic interactions. If this number were different, the very physics that allows atoms to form and stars to shine would fall apart. Yet some theories suggest these pillars of reality might not be fixed. They could have shifted slightly over the vast expanse of cosmic history. This is where the filaments become a cosmic ruler. The warm, hot intergalactic medium within them contains specific elements like oxygen and carbon. When light from a distant quasar passes through a filament billions of light years away, these elements absorb very specific colors from the light, creating a unique fingerprint. The precise position of these absorption lines in the spectrum depends directly on the value of the fine structure constant at that moment in the universe's past. By comparing the fingerprints from filaments at different distances, and therefore from different eras, astronomers can check if the constant has changed. It is like finding a series of cosmic clocks, each set at a different time, and checking if they all tick at the exact same rate. A single filament gives a single measurement, but the web's immense scale provides a network of checkpoints spanning billions of years. The implications of a detected change would be revolutionary, forcing us to rewrite our most fundamental theories of physics and reconsider the very stability of reality. This transforms the cosmic web from a simple structure into the most expansive experimental apparatus in existence, a natural instrument probing the deepest rules of the cosmos. This grand cosmic architecture might be a magnificent illusion. The very filaments we have been mapping could be less like solid bridges and more like a trick of the light, a pattern our minds impose upon a chaotic universe. This is the profound philosophical question at the heart of the cosmic web. Is it a real physical structure or merely a statistical ghost? From one perspective, the filaments are undeniably real. They are vast concentrations of dark matter and hot gas that exert a powerful gravitational pull, guiding the formation and movement of galaxies. We can measure their mass through gravitational lensing and detect their hot gas through X-ray emissions. They are physical entities in every sense that modern cosmology can define. Yet another viewpoint challenges this reality. When we look at a map of the cosmic web, we are not seeing a continuous, solid thread like a strand of silk. We are seeing a dense line of individual galaxies, and our brains connect the dots. The filament is the pattern that emerges from the collective positions of countless galaxies, much like seeing the shape of a constellation in the random scatter of stars. In this view, the filament itself is not a distinct object. It is the name we give to the tendency of galaxies to align along certain preferred directions. This debate touches on the very nature of reality in an expanding universe. As space itself stretches, the distances between galaxies increase. Are the filaments stretching with space, or are the galaxies within them simply moving farther apart along the same statistical lines? The answer depends on whether you see the cosmos as a collection of discrete objects or as a continuous fluid of matter and energy. Most cosmologists today embrace a middle ground. They see the cosmic web as an emergent phenomenon. It is a real structure that arises from the collective behavior of its parts, much like a whirlpool in a river. The whirlpool is a real, powerful current that can pull objects in, but try to grab hold of it and your hand passes through water. It has no solid, independent existence apart from the flowing river. Similarly, the cosmic web is a real pattern of density and gravity, but its apparent form is shaped by how we choose to map it and the scale at which we observe. This leaves us with a humbling thought. The universe's largest structure may fundamentally be a matter of perspective, a beautiful and powerful pattern that is both real and imagined, a scaffold for the cosmos that challenges our very definitions of what it means to exist. Our cosmic maps might be missing entire cities in the dark. Threaded through the luminous filaments of the web could be a hidden population of dark galaxies, cosmic ghosts made almost entirely of dark matter. These would be islands where the dark matter gravitational pull was strong enough to form a structure, but where far too little ordinary gas was gathered to ignite the fires of stars. They are the ultimate failed galaxies, drifting silently in the vastness, invisible to our telescopes because they emit no light. Their existence is more than just a curious speculation. Finding them could solve one of cosmology's lingering puzzles. Our best simulations of the universe predict that the cosmic web should be far more crowded with small, dwarf galaxies than we actually observe. There is a glaring mismatch between the number of dark matter clumps the simulations create and the number of small, shining galaxies we can actually find. Where are all the missing dwarfs? The answer may be that they are not missing, but merely dark. These dark galaxies could be the invisible counterparts to the faint dwarfs we do see, completing the predicted population and finally bringing our cosmic census into alignment. But how do you find a galaxy that gives off no light? Astronomers must rely on the subtlest of gravitational effects. If a dark galaxy passes in front of a distant star, its unseen mass could briefly warp the star's light, causing it to momentarily brighten in a phenomenon known as gravitational microlensing. Alternatively, if one of these ghosts lurks near a bright galaxy, its gravitational tug might distort the visible galaxy's shape in a way that betrays the presence of the unseen companion. Confirming their existence would be a monumental discovery, revealing a shadow universe of structures that have lived alongside us completely unseen. It would force us to ask a profound question: is the universe we see merely the illuminated fraction of a much darker, hidden whole? The pattern of galaxies and voids we see today might be the only one of its kind. This cosmic fingerprint was set in stone by the random quantum ripples that flickered into existence at the very beginning of everything. Those minuscule fluctuations were the universe's unique signature, a random roll of the cosmic dice that determined where the first filaments would thicken and where the great voids would expand. From that moment, the fate of our entire observable universe, the placement of every galaxy cluster and the curve of every dark thread was locked in. This leads to a staggering possibility. If the initial conditions were even slightly different, the cosmic web would be unrecognizable. A slightly smoother start might have resulted in a sparse, wispy web with few galaxies. A more jagged beginning could have created a dense, tangled knot of filaments, with galaxies packed so tightly that life might never have found a quiet corner to emerge. Our specific cosmic architecture, with its balance of great walls and vast emptiness, could be a direct reflection of that one in a trillion initial state. This uniqueness forces us to look beyond our own universe. The theory of the multiverse suggests that our cosmos might be just one bubble in an infinite froth of universes, each with its own random set of initial conditions and its own fundamental physical laws. In that endless landscape, other cosmic webs would exist, each utterly alien to our own. One universe might have a web woven from brilliant, continuous walls of light with no voids at all. Another might be a lonely, diffuse haze, its galaxies scattered like distant, isolated islands with no connecting threads. The very strength of gravity or the nature of dark matter could be different, giving rise to webs with 2 dimensions or 4, or structures we cannot even begin to conceive. Our universe's fingerprint, then, is not just a map of what is. It is a profound clue, a single data point suggesting that the reality we know is merely one possible expression of a much vaster, more varied cosmic tapestry. The serene appearance of cosmic filaments hides a hidden chaos. Deep within these great rivers, the gas does not flow in a smooth, laminar current. It churns with violent turbulence, a disorder born from the universe's most powerful forces. This turbulence is generated by the relentless gravitational pull of dark matter, which accelerates gas to incredible speeds, and by the colossal shock waves that ripple through the filaments when they collide or when gas slams into forming galaxy clusters. It is the cosmic equivalent of a peaceful mountain stream suddenly transforming into a raging, white-water rapid, but on a scale spanning millions of light years. This invisible turmoil has profound consequences. For a galaxy waiting at the end of a filament, this turbulence can be both a blessing and a curse. On one hand, the churning motion can prevent the gas from collapsing too quickly, regulating the birth of stars and preventing a galaxy from burning through its fuel in a single, frantic burst. It acts as a cosmic pressure valve. On the other hand, if the turbulence is too extreme, it can heat the gas through countless microscopic collisions, making it too hot and energetic to coalesce into the dense clouds that form stars. It can effectively stifle star formation before it even begins, leaving a galaxy starved despite being in the path of a cosmic river. This delicate balance between chaos and creation is one of the greatest challenges in modeling the universe. Our most powerful supercomputer simulations struggle to capture the full, chaotic nature of this turbulence. The motions occur on scales too small for our cosmic scale models to see, yet their collective effect shapes the fate of entire galaxies. It is like trying to predict the exact weather pattern across an entire continent without being able to model every gust of wind and every tiny cloud. This limitation means our picture of the cosmic web is still incomplete. We see the rivers, but we cannot yet predict their flow with perfect accuracy, leaving a fundamental question unanswered. Is the universe's grand design ultimately shaped by the invisible, chaotic heart of its greatest structures? Every river carries more than just water, it carries the history of the land. The cosmic web is no different. Flowing along its dark filaments are the heavy elements forged in the hearts of stars and scattered by their violent deaths. This is the chemical enrichment trail, a record of cosmic pollution that tells the story of star formation across the ages. When a massive star explodes as a supernova, it does not simply vanish. It seeds its surroundings with a cloud of newly created elements: oxygen, carbon, iron, and silicon, the very building blocks of planets and life. These enriched materials are then swept up by the gravitational currents of the cosmic web, entering the rivers of gas that flow along the filaments. Over billions of years, this process transforms the pristine hydrogen and helium from the Big Bang into a chemically rich broth. By studying the composition of the gas within a filament, astronomers can read this history. They use distant quasars as cosmic flashlights. As the quasar's light passes through a filament, the heavy elements within the gas absorb specific colors, leaving behind a unique chemical fingerprint in the spectrum. The strength and variety of these absorption lines reveal which elements are present and in what quantities. A filament rich with iron and oxygen tells a story of numerous supernovae, a region where star formation has been vigorous for eons. A filament with only trace amounts of heavier elements might be a more pristine, undisturbed structure, a relic from a time before widespread stellar pollution. This turns the cosmic web into a sprawling historical archive. By tracing the chemical enrichment from the earliest, most distant filaments to the richer, more polluted ones nearby, we can piece together a timeline of how the universe went from a simple, pure state to the complex, element-rich cosmos we inhabit today. It is like taking core samples from an ancient forest, each layer revealing a different chapter in the life of the ecosystem. The great mystery is not just what the filaments contain, but the story of creation and destruction written in their elemental soul. This silent river of galaxies is not flowing as we expected. Across immense stretches of the cosmos, entire clusters and superclusters are moving together in a vast, coherent stream, as if pulled by a cosmic tide. This is not the gentle drift of the universe's expansion, but a mysterious, directed flow on a scale that defies easy explanation. Astronomers call this the dark flow, and its existence points to a startling possibility. Our local universe might be caught in the gravitational current of something immense and unseen lying far beyond the edge of our observable horizon. The Great Attractor was the first such mystery discovered, a gravitational anomaly in the direction of the Centaurus constellation, pulling our own Milky Way and thousands of other galaxies toward it. But for every great attractor, there must be a source and a sink, a push as well as a pull. This is where the concept of the Great Repeller emerges, a vast, under-dense region of the cosmic web whose immense emptiness might be exerting its own strange influence. Think of it not as an anti-gravity force, but as a gravitational hill. While a massive filament acts as a deep valley pulling matter inward, a colossal void is a high plateau. Matter naturally flows away from the hill and down into the valleys. A great repeller would be the ultimate cosmic hill, a void of such staggering scale that its lack of gravitational pull effectively pushes galaxies away, steering them toward denser parts of the web. The evidence for these flows is etched in the cosmic microwave background. As these gigantic structures move through space, their motion imprints a subtle temperature shift on the ancient light, a faint Doppler signature of their collective journey. The problem is that the sheer scale and coherence of this motion challenge our standard model of cosmology. The structures needed to generate such a powerful flow would have to be unimaginably vast, perhaps larger than any known supercluster, and located in regions of space we cannot yet see. Are we being influenced by the shadow of a neighboring universe, or is there a flaw in our understanding of how gravity operates over these immense distances? These great flows force us to confront the limits of our cosmic map. We have been charting the visible filaments and voids, but perhaps the most powerful architects of motion are the structures we have not yet found, the ghostly giants hiding in the darkness just beyond our sight. The perfect geometry of the cosmic web might be more than a simple structure. It could be a vast thinking mind. This speculative mystery asks if the filaments of the universe function as a cosmic neural network, a celestial brain where information is processed on a scale beyond human comprehension. The similarities are startling. Just as the human brain is a web of neurons connected by axons, the universe is a web of galaxies connected by dark matter filaments. In both systems, the nodes, whether they are galaxies or neurons, are the active processing centers, while the filaments are the communication pathways that link them together. This is not to suggest the universe is consciously aware, but that it might operate on a similar principle of interconnected complexity. The flow of energy and matter along these cosmic threads could be a form of data transmission. A galaxy flaring with a burst of star formation might send a gravitational ripple or a wave of radiation down the filament, influencing the behavior of other galaxies in the network. The entire system could be engaged in a constant, slow-motion feedback loop, regulating its own growth and structure over billions of years. This idea pushes the very definition of information. What kind of data would a universe process? It could be the simple physical state of its own components, the density of matter, the strength of magnetic fields, or the rate of star formation. This constant dynamic exchange maintains the equilibrium of the cosmic web, a self-regulating system of unimaginable scale. If this is true, then the great cosmic voids are not empty, they are the silent spaces between the thoughts of the cosmos. This transforms our view of reality from a static architecture into a living, dynamic process. Are we merely tiny observers within a single synapse of a universal mind, witnessing the slow, majestic firing of its thoughts? Even our most advanced technology cannot fully capture the universe's grand design. We confront a fundamental limit in our quest to understand the cosmic web, the sheer inability of our most powerful supercomputers to simulate its true complexity. These digital universes, running on machines that cost millions to build and power, are our virtual laboratories. They allow us to rewind time, test theories of dark matter and gravity, and watch as digital filaments slowly form from a primordial sea of particles. Yet every simulation is a compromise, a simplified version of reality. To model the entire observable universe from the Big Bang to today, scientists must choose their focus. They can simulate a vast volume of space, but only with a coarse resolution that treats entire galaxies as single points. Alternatively, they can zoom in on a single, forming filament with incredible detail, but only by ignoring the vast cosmic context that shapes it. This is the great trade-off, scale versus detail. It is like trying to draw a map of an entire continent while also capturing every single tree and stream. You can have one or the other, but not both in perfect fidelity. The most significant gap lies in the turbulent chaos within the filaments themselves. The supercomputer models are simply not powerful enough to calculate the trillions upon trillions of microscopic interactions in the swirling gas, the very turbulence that dictates whether a galaxy is starved or feasts. Our simulations show us the cosmic rivers, but they cannot yet accurately predict the flow of every current and eddy within them. This limitation is more than a technical hurdle. It is a profound statement about the nature of reality. The fact that the universe's complexity outstrips our greatest machines suggests that the cosmic web may hold depths of chaos and order we have not yet even begun to conceive. What subtle rules governing the birth of galaxies are we missing because our digital universe is still just a shadow of the real thing? The final and most personal mystery brings our journey home. Where exactly does our own Milky Way galaxy reside within this immense cosmic architecture? After mapping the universe's grand design, we must now locate our own address. The answer reveals that we are not at the center of anything, but reside on a quiet suburban street of the cosmos. Our home is part of the Laniakea supercluster, a vast collection of over 100,000 galaxies spanning 500 million light-years. Laniakea means immeasurable heaven in Hawaiian, a fitting name for our celestial continent. Within Laniakea, we are not at the bustling core, the great attractor that pulls everything inward. Instead, our Milky Way lies on a faint outer filament, a spur of the cosmic web that streams away from the central density. We live on a galactic country road, not in the metropolitan heart. This local perspective profoundly shapes our view of the universe. Our position on this relatively quiet filament means our night sky is not ablaze with the light of countless nearby galaxies. We enjoy a certain cosmic privacy, a dark sky that allowed us to first dream of the stars without being overwhelmed by our crowded surroundings. It also means the river of cold gas flowing to us is likely a gentler stream, not a raging torrent, which may explain our galaxy's steady, but not explosive, rate of star formation. Our place in the web is humbling. We are not special, not central, just one of countless galaxies strung along an invisible thread in an unimaginably vast structure. The greatest mystery of all might be how this quiet, unremarkable location on a cosmic filament became a place where the universe could wake up, look out, and begin to understand its own beautiful, terrifying, and hidden design. From the ghostly touch of dark matter to the echoing whispers of the first sound, these 25 mysteries define our quest to understand the cosmos. We have journeyed through the invisible framework that binds the universe, confronting the enigma of its missing atoms and the turbulent rivers of gas that fuel galactic life. We have questioned the stability of physics itself within these vast corridors and pondered if the great web is a real structure or a magnificent pattern we impose upon the void. We have traced the chemical history of the stars along these threads and felt the pull of unseen giants in the darkness. Each mystery, from the cosmic neural network to the final fate dictated by dark energy, represents a frontier of human curiosity. The filaments of the cosmic web are more than just the largest structures in existence. They are the ultimate laboratory, the grandest archive, and the most profound puzzle. They challenge everything we think we know about reality, so we turn this final question to you. After this journey through the hidden architecture of the universe, which of these 25 cosmic mysteries captures your imagination the most? Share your thoughts and never stop looking up at the stars, wondering about the invisible threads that connect us all to the grand tapestry of everything.